first of all, I'm thrilled to be back at Purdue. My daughter is a early 90s grad of the aero department. So, as a matter of fact, she said she went to school in this very building. And then I used to give a talk to the mechanical engineers for a number of years, the sophomores. So, but it's fun to be back. And frankly, I don't recognize the place. It's changed totally since the last time I was here. But what I thought I would do today is give you a little bit of an idea of what I did at GE so that you know where I'm coming from. But really the purpose of what I'm going to talk about is like the title of my talk is Engineering in the Big Leagues. And when I say big leagues, it's basically from a perspective of somebody that's worked in the aviation industry. Because I think the aviation industry is significantly different than most industries because of the level of responsibility that goes along with flying people in airplanes. So that's what I mean about that. So in any case, well, as Bill said, not only did I work in the aviation industry, I played in the aviation industry as well. And I just thought I'd show you these briefly. The airplane up on the left is a B-35B Bonanza that my wife and I flew all over the country. We were up in Alaska with it 3 times. And I'm an instrument-rated and commercial-rated pilot. So that was one way that we participated in the aviation industry. And then when I retired, I couldn't stay away from me either, so I built the airplane on the right. It's a Vans kit. And if you're into airplanes at all, I encourage you to go look up Vans aircraft and see what they are. But it's a fun little airplane. It's a 200-mile-an-hour, really fun airplane to fly. And I since sold that airplane to a Delta pilot who was an F-16 Air Force guy, and he's now a Delta pilot, so he's flying that airplane around now. And then we built the red one on the bottom is an RB-8A, which is a tandem airplane. And that's got avionics in it that won't quit. It took me 6 months to wire that airplane. But the message is, I'm an airplane nut. I mean, that's a reality. So with that, we'll see if we can get to something a little bit more serious. So what I want to do from here on out is I'm going to talk about an airplane accident. And the events of the last 2 weeks makes this a little bit fresher in everybody's mind, but I'm going to talk about an airplane accident that happened in 1989. And one that I was associated with for a number of reasons that I'll tell you about when we go through it. But as we go through there, I want you to pay attention to the words that I've got emboldened on the chart. Trust, responsibility, risk, and decisions. Because when you're engineering in the aviation industry, all of those things come into play in a big way. So with that, Bill, you tell me when you think that video will go.
It can take a couple minutes.
All right. I'm going to go back to July 19th, 1989. There was a United Airlines flight boarding in Denver, Colorado, going to Chicago. It was a beautiful afternoon and day, and the airplane was a DC-10-10, which is a 3-engine airplane that I'll show you a sketch of. A 3-engine airplane where one of the engines is in the tail. The engine was a CF6, a GE CF6-6 engine that was designed, basically the engine was designed in the late 60s. This particular engine that we're going to talk about today was built in 1971. And the flight was Denver to Chicago, as I said. And on board the airplane were 296 passengers and crew. Well, what I don't have on the chart is United Airlines had a special that day. They had a special where children could fly for $1. So there were 50 children on the airplane. So you remember the words that I told you to remember. Trust. The people that got on that airplane trusted us. Not just the engine people, not just the airplane people, not just the pilots. They trusted everybody. They trusted the system with their lives. Along with trust comes responsibility. So all of us in the industry had a responsibility to protect their lives. And then we'll get to the word risk in a minute. But anyhow, there's the flight. And what happened on that flight is they took off, and after about an hour or so in the air, there was a large explosion at the back of the airplane. Obviously, it got everybody's attention. The crew looked at their instrumentation. They saw that the tail engine had failed. But then they saw something else. They saw that the hydraulic pressure on all 3 hydraulic systems was going down to 0. What that means in an airplane, fundamentally the hydraulic system on an airplane of this type connects the pilot to the airplane. So if the hydraulic system fails, the pilots are no longer flying the airplane. Literally, the airplane is flying itself. So what happened? The airplane started to drift off in a little bit of a bank, and then it would drift back a little bit. And there was a United Airlines check captain sitting in first class. He was deadheading between Denver and Chicago. He went up into the cockpit, and between him and the crew, they figured out that they could control the airplane a little bit by manipulating the throttles on the wing engines. So they would power up one engine and power up the other, trying to maneuver the airplane. And they had some little bit of control to the airplane. This is the airplane so that you know what we're looking at. And I guess I can use this. There's the tail engine and the tail. But looking down on the airplane, you'll see that the engine is sitting over the horizontal stabilizer for the airplane. I think the next chart will show you. This is what happened. Oh, it's not going to play.
Let's see.
You're killing me, Bill. Come on, you're killing me. That should play. That should be loaded up here. Oh, Bill.
I'm flying with somebody else's computer.
No, you got to go back up.
I'm trying.
We'll get it. Hang on. Man, I'm jumping today.
Okay, so click on that. Click on the play.
Watched 111 people die. It's been 28 years since that happened. I can hardly talk about it. At that point in time, I was the engineering manager for the CF6. That was one thing. But that really wasn't the problem as far as I was concerned. Is somewhere around 1983, I was working on a problem that we had with the metal titanium. And it turns out, well, let me go to the design of the engine a little bit so to give you a perspective. The part that had failed, that actually caused this accident, that initiated this accident, I need to use this. Oh man, the pictures aren't very good. Is this metal part right here? This is a round disc. It's a metal part right here, and its purpose in life is to be the structure to carry the fan blades that are in the front of the engine. These are the big fan blades that you see when you look in the front of a big jet engine. And fan blades are about this big. There's this round disc in the bottom of those that carry those loads. All right. That metal is titanium. The airplane crashed. Right after the crash, it was pretty apparent that the front of the engine was gone, and more than likely the problem was that the fan disc itself had failed. When the fan disc fails, it's a 215-pound piece of metal, by the way, and the loads in it are big. They're probably running somewhere, I don't know the numbers for the fan, but in the turbines, they're somewhere around 1 million pounds, by the way. You can think of the strain energy pileup in that thing. But anyhow, it was pretty obvious that the fan disc had failed. It was gone. It was, it was in a cornfield somewhere over Iowa. So that's what happened there. And then when that happened, all the fan blades came out of the engine and hit This is a better picture of the disc, by the way. Here is the fan disc in a little bit. The fan blades are not in this picture, but this is the round circular fan disc, and that's a cross section of it right there. That's the front of the engine. But when that part failed, the debris that came out went right through the nacelle, hit the tail of the airplane. This is looking down on the end. Here is the fan disc in the airplane. This is the hydraulic systems running through the airplane, and the debris from that hit all 3 hydraulic systems, and that's what's that's what the reason that this airplane crashed. The fan disc was in the field. We were trying to figure out what we were going to do. People were looking for the fan disc. So what we did is there were, as I remember, 5 other engines with fan discs made from the same ingot of material, from the same billet of material as the failed fan disc. So we went and got those engines. We got the fan discs from those engines, and we cut them up to look at the microstructure of the metal. My materials guy was in the materials lab, and I was in another building, and I was walking across the parking lot one August afternoon, and I saw Bill come out of the lab, and he had a cross section of one of these discs in his hand. And what they had done with it, they cut the disc in a cross section very much like that picture I showed you, and they etched the surface to see the microstructure of the material. It was horrible. It was horrible. When I saw it, I wanted to be sick. The reason is now those of it who had been working on the titanium problem back in 1983 knew pretty well that the problem that we had been working on back then had initiated this failure. I can't tell you how that makes you feel when something that you had been working on that you were trying to fix causes kind of a problem. It's like I say, it's something I pretty well can't describe to you. We eventually found a fan disc. This is what it looked like. This is what it looked like. You can see this is the broken, probably the first piece that came out, the fan blades, and then the rest of it came out, but that's the failed fan disc. And then I'll show you something else. By the way, somebody just recently gave me this picture. I gave a talk like this to the GE folks, trying to talk to them about doing a good job, frankly. But anyhow, one of the materials people came up to me and he gave me a full-size picture of this fracture surface. This is the actual disc that was in that engine. You see this little black spot down on the bottom of the disc? This is a 215-pound piece of metal, by the way. It's a big chunk of metal, about that big around. That defect down there initiated that failure. And I took this picture and I put it together. There is the defect over here, and that is a ballpoint pen there. That's the actual size of the defect that caused this accident. That disc had 15,500 flights on it. It was about 1,000 cycles away from its life limit. It had run from 1971 to 1989. So that's to give you an idea of when we talk about quality and process capability and all those things in the aviation world. These are the kind of things that we have got to be concerned about. And to have a defect of this size in a part that big and have people's lives directly tied to that, it just brings a whole new perspective about how you do your business. So what I'm going to do is I'm going to divert a little bit because obviously there's been a lot in the media. I'm sure you folks have seen the recent failure where a CFM56, which is a GE SNECMA engine, failed on a 737. Debris came out and hit the window, and this unfortunate lady got sucked out the window and she lost her life. And so I thought that I would spend a minute or two and give you a little bit of a primer about jet engine design and how we manage problems like this. This is a cross-section of the CFM56 Failure, which is the same engine that was on the 737, by the way. Here's the fan section, there's the fan blade, and in this case, the disc looks like this. It's a little bit different shape this than what I showed you on the CF6, but that's the structural part. That's the structural part that carries the load of those fan blades. What happened on the 737 event is the fan blade itself failed down at the root, down here in the dovetail section. And it failed from a problem called low cycle fatigue, and I can bore you with a lot of reasons why that happens. It doesn't happen, which is not the point of it. But the message I want to give to you here is the engine is designed to take that kind of failure. And when I say it's designed to take that kind of failure, it will shut down, but the engine is designed not to release any high energy particles. In other words, it is designed not to release that fan blade so that it goes and does things like puncture the fuselage or hit hydraulic lines or whatever. We actually ran that test twice. In both cases, it passed. When I look at the pictures on the internet of the actual failure of the 7.3, my reaction as a design engineer for jet engines, I say it was the perfect fan blade out event. You'll only see one blade missing. It's just perfect. The containment case contained the blade. This is the containment case up here. That's a big casing around it. You can see this ring up on top of it. That's there so that it helps containing that blade when it comes out. Apparently what happened, and this is my opinion by the way, this is not GE, this is not Boeing, this is not anyone else, but this is this layman's opinion looking at the internet. My read on this is when that fan blade failed, for some reason, it broke the inlet. The inlet is this piece right here, and then there's a cowl wrapped around it. It goes all the way back to here. These pieces came out, and that's what hit the airplane, and that's what took the lady out. The difference between this and the Sioux City accident that I talked about is in the Sioux City accident, the disc failed, not the fan blade. The disc is a life-limited part. It's low cycle fatigue limited. It has a certain number of cycles on it. If the material is the material that you expect when you design it, like a material without any defect in it, it will have a certain number of cycles which you will allow it to fly, and then it is removed. The fan blades are not life-limited parts because they are subject to all kinds of things that discs aren't subject to. They're subject to birds, they're subject to debris coming into them. There's all kinds of reasons why fan blades will fail. We know fan blades will fail. Okay? That's why the engine is certified that when a fan blade fails, it should not come out of the engine. That's the difference between the 737 event that you saw this week and the Sioux City event. The Sioux City event, the disc failed. There was nothing going to contain the disc. It came out, it hit the hydraulic lines, and that's why it failed. Okay, all of that being said, enough about CFM56s. Let's go back to the fan disc. Let's talk about processes. Let's talk about what people did during this and what this looks like. Anybody here in the materials world? Anybody? Nobody, so no one's going to, uh-oh, you're going to test me on what I know about titanium. All right. You tell me if I did something wrong. I'm going to give you a very high-level view of how titanium is manufactured. Okay? And I want you to remember the word risk. I want you to remember the word risk. I talked to you about trust. I talked to you about responsibility. Now I'm going to talk to you about the word risk. I'm going to tell you about titanium. First of all, the disc was made in 1971, and obviously the technology for melting titanium back in 1971 is not what it is today. That doesn't say the process that makes titanium today is perfect. It's not. It's much better, and the inspection techniques are much better, but it's not perfect. Titanium was made back then. I think it's still made today the same way with a process called the Kroll process, which starts with an ore coil rutile. They react that with chlorine to come up with something they call TICL, TiCl4. Now you're going to go to your high school chemistry, TiCl4. In a convoluted sort of way, at least this mechanical engineer's perspective on titanium, especially TICL, TICL is a clear liquid at one point in time. It's a clear liquid, and I keep saying any metal that at one point in its life was a clear liquid can't be that good. Anyhow, TiCl4, they react it with sodium, and sometimes magnesium, but sodium. What's your high school chemistry say? TiCl4 plus sodium gives you what? Gives you titanium plus salt. What this looks like, they do this in a big cauldron, by the way. It's a giant cauldron. It's probably half as big as the width of this room, and it's about as high as the ceiling, maybe not quite that high. It's a giant cauldron. They do this reaction, they cool it down, they open the lid, and you look in there, and there is this giant piece of titanium which is filled with salt. And it's really a strange looking thing, because if you look at the titanium itself, it actually looks like sponge. If you take the salt out of it, it looks just like sponge. Just, if you wash your car with a sponge, that's what it looks like. And the way they get this out of the cauldron, are you ready for this? They jackhammer it out. They take a jackhammer and they pound this stuff out, and it comes out in big pieces and small pieces and dust and all kinds of stuff. They take this stuff and they use water to leach out the salt, and now you're left with sponge. And it's all these rocks and big pieces and little pieces. They crush it down to relatively consistent pieces, maybe this big, some smaller. And then they run it over a conveyor belt. And they have, at least when I was there, they have one person on this side, human factors, one person on this side and one person on this side. And I was telling Bill at lunch, it kind of looked like, how many people have seen the I Love Lucy show where the Lucy's on one side and Ethel's on the other, and the candy is coming out and they're looking at the candy for quality? That's what this looked like. I mean, here comes out the sponge, and this guy is on this side, and another person is on this side, and they're looking. What are they looking for? They're looking for a compound called hard alpha. You know that little black spot on the bottom of that disc that caused that failure? It was hard alpha. I went up there and I looked at that, and I said, "Geez, this can't be." That's the way they did it. So then they take these pieces of sponge, they sprinkle in a little alloy material, aluminum, vanadium, whatever the alloy they're going to make. They compact it down into what they call a brick, and the brick is about as wide as this computer, and it is about that high. It's literally a brick. They take those bricks and they stack them up, boom, 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 into a big long thing. I'm trying to remember, 15 feet long, and they weld the bricks together. They weld them together. Now you got to go back to the chemistry and the characteristics of titanium. It turns out that titanium is what they call a getter. What is a getter? A getter is a material that when it gets hot, it sucks up oxygen. What happens to titanium when it sucks up oxygen and it forms hard alpha? What's bad about that? Hard alpha is brittle and it's weak. Brittle and weak doesn't go good with high stresses. All right. So now you got a process that involves a lot of high temperature. Oh, wait, I got to finish first. So to hold these bricks together, they weld them. Well, the last I knew, welding was a high temperature process, right? The guy's got a torch, he's going to go down here, he's going to weld. So they put a little tent over it, and then they bleed in some argon as an inert gas to keep the oxygen away from the weld. Pretty agricultural way that they did that. So here's another chance to form a hard alpha. Remember the word risk. Here's another risk in the process. Okay. You had human factors on the inspection for the thing. Now you got the guy with the welding and the tickle and the getter, and he's welding on it. Okay, fine. Now they take that stick, they put it in a furnace, they melt it. In this case, they melted it twice. Today, they melt it 3 times, and then they draw it down into a billet. It's a nice long. I think this was a 17-inch billet, so a billet about that big in diameter, about 8-10 feet long. I can't remember how long it was. And they inspect it. Back in 1971, they used what they call contact ultrasonic inspection. Contact ultrasonic inspection, basically you've got an ultrasonic probe and you rub it across the surface without any medium between the surface, the metal, and the contact. contact ultrasonic is known to be a not a very sensitive inspection technique, but that's the way it was done back in 1971. Didn't find anything, by the way. Oh, and I forgot another detail about hard alpha. Sometimes it's cracked, sometimes it's not cracked. If it's not cracked, I don't care if they see the hard alpha. They can't see it in reality. If it isn't cracked, ultrasonic's not going to see it. All right, another detail. Okay, so here's the billet. They contact ultrasonic, it's fine. They cut it up into mults. They put it to the forge shop. The forge shop forges it. They send it to the machining shop. The machining shop turns it down into another, they call it an ultrasonic envelope, where now they immersion ultrasonic. Okay. Immersion ultrasonic is done in water, where there's a better contact. It's a much more sensitive inspection than the billet. Again, if the hard alpha is not cracked, you ain't gonna find it. Okay. They machine the part, and they FPI inspect it. How many are you familiar with the term FPI? Nobody. Oh, God. FPI is a human process. You familiar with FPI at all? No? Okay. I got to explain FPI then. What they do is they have a fluid. They have a very inviscid fluid. They clean the part. They have a very inviscid fluid, and the characteristic of the fluid is it glows in black light. What's black light? Blue light. Whatever. Oh, okay. This stuff glows a bright orange underneath a black light. So if you have a part with a crack on the surface, you dip it in this fluid, you take it out, you clean it off, but you don't clean it off perfect, if you will. You put a black light on it, and if it has a crack on the surface, it will show up as this bright, day glow kind of orange. Okay. That's a visual process. And by the way, the part has to be, the defect has to be on the surface, and it has to be cracked. Okay. And it's done by a human. Okay. This part passed. Otherwise it wouldn't have gotten shipped. It passed. It went into service. It went into service and was inspected in the field a number of times by fluorescent penetrant inspection. It was inspected, are you ready? 1 year before the accident. It was in the United shop. And after the accident, we figured out at the point in time where it was in the United shop for FBI inspection, it had a 1/2 inch long crack in the bore. The crack was sitting there. It was FBI inspected, human factors. The inspector missed it. He missed it. That's why that part failed. Go back to the word risk. You go back through this process. You look at the places where the process gives you the potential to put in defects. There is some number of risks. And the way that I looked at that is I always thought of it as the world is a mound of titanium that somebody sprinkled in a few little defects. And the task was to find them. How did we go to find them? 2 ultrasonic inspections and FPI. That's the way the business was done at that point in time. But that says, the way I describe the aviation business today is I call it aviation's big lie. What's aviation's big lie? And I don't mean to frighten you from flying airplanes, by the way. Aviation's big lie is that it's safe. The reality is aviation is not safe. Aviation is a world of managed risks. It goes from a piloting standpoint. You go weather, you go all kinds of things. Training, you go all kinds of things. You go manufacturing processes, risks associated with that. Just aviation is a world of managed risks. That means that the people inside this endeavor have got to be responsible. And being responsible means that they have to make responsible decisions. So, let me see if I got everything covered here. I got all that, visual spec, contact, okay, yeah, okay. Harsh realities of aviation industry. It's unforgiving. I mean, you make a mistake here, it's a big mistake. People on the airplane trusted us. And again, it's the big us. I talked about responsibility. I talked about risk management. Recently written a book. I don't know if any of you have seen it or not. One of the things I talk about in the book is I talk about what I call the three worlds. I talk about the outside world, I talk about the corporate world, and I talk about the personal world. The corporate world, you know, people think companies are human for some reason. I mean, it's a perspective that I seem to get off the TV set. They think that corporations are in themselves human beings. They're not. The reality is corporations are people. It's the people inside the corporations that make the decisions. The other thing, and I think you sensed when I put the video up here of the airplane crashing, the other reality is just because that you are one of the members of this inanimate corporation doesn't mean that you don't have some personal responsibility here for what you've done inside this corporation. I didn't talk about this, but the reason that I'm so involved in this thing is because at one point in time I had an opportunity to put another inspection in before that disc failed, and I didn't take it for a number of reasons which I won't bore you with. But I haven't forgotten that from my own personal standpoint. But the message I want to leave you is this is not an abstract world that you're living in. You know, when you get into a business like this is not an abstract world. You know, I was telling Dr. Landry and Bill today at lunch that probably the biggest joy that I got out of working on jet engines over the year at GE is I always felt that I owned the product. I mean, it's a sickness almost. I mean, you know, it just really felt that I owned the product that I worked on. That's the good news and the bad news. The bad news is when something like this happens, you own the product. It's something you'll never forget. And you know, I don't see anybody talking about this. That's why I'm telling you. All right, I'm going to go to my book a second. And I talked about decisions. You know. In my book, I talk about there are 6 things that influence the way people make decisions. And I'm going to talk about this from what I'll call a corporate environment, if you will. And the 6 things are values, culture, goals, measurements, perception of risk, and organizational complexity. Bill and Dr. Landry were telling me about the industrial engineering department here and how you folks are focused in on efficiency and all that. And of course, I came back to him and I said, but why aren't you talking about quality? And maybe I'm being harsh on you guys, so I'll apologize right now. You know, and my message was, you know, and their comeback was, well, it's just assumed. They just assume that we're going to do it quality-wise. And my message from if you're in the management of a company, you can't let your overarching value for the organization be silent. People will forget it. I'm going to go back to pre-Sioux City. See, I told you to get me talking about stuff. I'm going to go back to pre-Sioux City. Let's go to 1973. There was an A300 flying somewhere in the world. There was a big compressor failure. Boom! It came apart. It was uncontained. Happened to be a titanium part on a GE engine. Nobody got hurt. The airplane landed safely. We found a hard alpha in that compressor disc. That was 73, 5 years later. In 1978, there was another one. Exactly the same thing. Hard alpha and a compressor disc, titanium. 1983, another one. And then not a week later, another one. In all four of those events, no one got hurt. What do you think the message was that sent us? It said it was all right to have those failures. That's pretty harsh language. It really wasn't quite that bad, but it basically gave us the perception that, yes, it was an engine shutdown, but it wasn't to what I call the doomsday event level. Yeah, we wanted to be safe, but we thought we were safe because we didn't hurt anybody. No one sat back and said, "Ooh, wait a minute here. Wait, our number one value is safety. Do we need to do something more?" You got to talk about it, is my message. If you're running a company, stand up and every now and then, and I mean relatively frequently, talk about the basic values of the company. I can, in my book, I got a write-up on Volkswagen diesel emission cheating. Read the chapter in the book on that. You talk about values or absence of values. There's a beautiful one right there. Culture. My definition of culture in a big organization is when an employee in the organization looks around and sees how the other folks in there are doing business, that they look at that as the acceptable way of doing business. Now, I'll put it in a school environment, an academic environment. If you look around and see the rest of the folks around you cheating, you're going to say, well, maybe I'll get away with that. I'll give you a clear message. If you're inside an organization like that, get out. I can say this, with all the things I showed you bad about, some of the aviation stuff I just talked about. I never, ever thought that I was working for a bad company that had the wrong values, the wrong perspective when I was working at GE. But if you see that, go somewhere else. Goals, that's easy. The boss says, gee whiz, to go to the Volkswagen thing, I want to sell diesel engines in the United States. That was the goal in the Volkswagen thing. Goals are easy. Measurements are putting numbers on goals. If your goal is to ship so many parts this month, right, then the measurement is, did you ship that number? Measurements are direct motivators for the employees. You think about it. If you're getting paid to make so many parts this month, right? And your boss is watching whether you're making those parts, you're gonna try your darndest to make it. And if you got the wrong culture in the business and you think it's okay to do something a little maybe not according to the book, you'll do it. And then I gave you the lecture on perception of risk. We had 4 failures that didn't hurt anybody. It dulled our sense of the danger that was involved with the kind of failures we were at. It dulled mine. When I made that decision not to inspect fan discs with ultrasonic, nobody had gotten hurt. And then the last one is organizational complexity. Sometimes these organizations are big and complex, and it just muddles up who is responsible. If it's a big organization, it's easy to say, well, that's not my job. That's Billy Smith's job over there, and he's thinking the same thing about you. I wrote about the Flint, Michigan lead in the water event. And you look at the Flint, Michigan lead in the water event, and you look at the what the role of the federal government was, the state government, the local government, and you say, oh my God, it hurts my head. Everybody just kind of was doing other stuff than thinking about keeping the people safe. So there are a lot of dynamics that go on inside big organizations. Some of them good, some of them bad. Be wary of this stuff, be wary of what's driving you. But you always got to go back to the top. In the case of Flint, Michigan, are we delivering safe water to the city? The reality is the people up there didn't care. My God. I talked about 1989. You just had an example this week of the CFM failure on the 737. It is, you folks are going to live in a different world than I lived in. You know, I've got a number. Have I got it in here? Yeah. I took the fatal accident rate in the U.S. in 1969, and I multiplied it by the number of airplane flights, commercial airplane flights in the U.S. last year. And if the fatal accident rate in the aviation industry was the same as it was in 1969 and in 2017, last year there would have been 620 fatalities in the U.S. This week there was one, and it was the first one since 2009. What do you think that has done to the perception of risk to the flying public? What do you think about when you get on an airplane? It is a different world than I engineered in. The expectation for the outside, from the what I call the outside world, is just completely different. The consequences are far more severe than they were back then. I don't know the exact numbers of what the Sioux City accident cost GE or United, but it was somewhere, and this is a guess number on my part, somewhere on the order of $60 million apiece. All right. The recent doomsday events, BP oil spill, Volkswagen, GM, the cheapest one was $20 billion, and the most expensive one was BP at over $40 billion. So if you forget this, what I'll call the moral responsibility of protecting people's lives, the financial consequences for these kinds of events is infinitely higher. And then you can tell how competent I was on computers, whatever. You know. But in writing my book, I was stunned at what I could find on the internet. Stunned. Every single email, practically every conversation was discoverable. When you get into a situation like this, nobody can afford to have presented the wrong perspective. Let me just put it that way. I go back to when I started GE, and GE's a really good company. I can't say. But I would see in design books, in design record books, you know, we had paper, engineers would draw cartoons and they'd have loose language in there, and it was, you know, and they were trying to be funny, or, you know, and the other, frankly, the other perspective is that no one was ever going to see it. That is not the world that you folks live in today. You cannot afford to be casual about what you do on your computers, in your communications, whatever. You simply don't let yourself get sucked into that, because when you're sitting in that courtroom, like I was sitting in that courtroom, and you got 20 lawyers trying to breathe down your neck, everything is going to come out. Everything is going to come out, and when they lay it down in front of you, You don't want to be ashamed of it, in spite of the fact that maybe you thought it was clever or whatever. Engineering is done differently. Same thing. Computers. I love computers. Man, I love them. I mean, you know, when I started in the business, you know what I had as a computer? I had a teletype machine that was talking to a mainframe that was as big as a building somewhere, you know, and we had IBM decks, you know, this big, and we'd go out in the snow and we'd drop them, and oh God, it was horrible. But what I have on the chart, Mother Nature doesn't care about the virtual world. Computers are in people's minds, and they reflect what's in people's minds. I was telling Bill and Dr. Landry at lunch, if there was one thing that I learned in 38 years of doing this kind of engineering work, is you've got to go out and look at the product. You've got to go see what the reality is. Don't trust the computer to convince you that what you've designed on the computer is really what it is in heart. Go look at what you're working on. The devil is in the details. That little defect in the bottom of that disc, the devil is in the details. The last thing about the internet thing that concerns me is the aviation world, especially the certified world, is a world of two things: configurational control and process consistency. When the engine and the airplane is certified, there is a configuration that is certified. That's what's been tested. That's what you proved works. That's what's been analyzed. You can't change it without doing all the same things over again. You can't do that. And then the other part of that is that the process, that detailed process that I told you about, making titanium or any other process that you got making these detailed kinds of parts, and now with additive, you know, with the computer additive, I mean, my God, you're making this stuff out of powder, right? It's too easy to change. Configuration control and process control in this kind of environment is absolutely vital. And when I look at how easy it is, if I'm additive making a bracket or whatever I'm making, I just change that software a little bit. My God, you know, I'll fix that problem. Big problem. Big problem. All right. How am I doing on time? Good. Okay, good. Some other differences between when I was working and when you're going to work. Organizations are far, far more complex. Far more complex. They're particularly international. I gave a talk to the GE engineers, and I frightened them even more than I'm frightening you. And I was telling Bill, and they had a camera like that, and at the end of the talk, I found out I'm talking to 5,000 people all over the world. I'm talking to China, I'm talking to Czechoslovakia, I'm talking to God knows who, Mexico, God knows who. That brings in how people communicate, how what I'll call our culture matches their culture, what this word means versus what that word means. You know, what kind of a society those people were brought up in versus what we're brought up with, what kind of expectations we have. It's a different world. The best advice I can give you relative to international is try to learn the culture of the people that you're working with. One, it's fun, by the way. I mean, it's fun. I mean, you know, I work with the French. Good Lord, that tested my patience, I'll tell you that. And the Japanese and the Russians and God knows what. And it's fun. And you know what? They're always interesting. And I mean, it's just really a kick. And frankly, we still have a lot of friends all over the world. This is one I love. BP, it was a perfect example of this. Complex projects involve a number of complex organizations. the airplane and engine interface is fine, or you could go airplane, engine, melter. You know, I mean, you can do this a whole raft of ways. And now we get into the organizational complexity kind of thing. Well, who's doing what? And the one I really love is who's responsible. Now, I'll tell you who's responsible in the lawyer sense. They'll just sue everybody. I mean, that's just the way the world is. They sued United, they sued GE, they sued everybody. Anybody with $1 in their pocket, they're going to sue. But that's really not what I'm after here. Again, it gets down to during the BP oil spill thing, Halliburton told BP, the Halliburton engineers told the BP engineers, don't do it this way. They said, don't do it this way. We think that's a problem. BP said, watch us. Did Halliburton have responsibility to go back to BP on the corporate level? I say they did. I say they did. Well, but why would Halliburton want to go to their best customer and say, you haven't got any clothes on? No, they didn't want to do that. Well, you know what happened to them? They got drug into it. It cost them a bunch of money, too. I've talked about this, values, cultures, and goals. It goes to, again, the culture of whoever you're working with. Who is responsible, who is in control, and then last but not least, IP. We ought to show the film before I get out of here. Not quite yet. I was telling Bill, I went to GE yesterday to give a talk to the thing, and I was going to carry my pitch in on my laptop. They wouldn't let me in. They wouldn't let me in because they're worried about the intellectual property that they've invested in their product getting to the wrong place. What you can store on your cell phone is infinitely better than what we could have stolen if we wanted to with a drawing or something. Infinitely better. I was telling Bill a story about it. I once had a picture of an 8.5 by 11 picture of a Russian engine that somebody had stolen, and he had his thumb in the picture when he shot the picture of the engine. I mean, that's what you could steal back in the 60s. Mm-hmm. Today, my God. I mean, IP control and protection is super important, regardless of what industry you're in. So, and I'll go through this pretty quickly. The aviation business, hey, what you do matters. Trust me, it really matters. It matters not only to the company, it matters to you. Don't let all the stuff that happens inside a big organization cloud your mind. Remember where you are. Remember why you're there. Remember the base reasons that you're there. When it comes to the aviation business, it's to get people safely from here to there. All the other stuff, yeah, that's problems. Yeah, but don't lose your perspective when you get all this other stuff happening. In spite of everything I tell you, I love what I did. I mean, I'm an airplane nut. I worked in the aviation industry. I was walking back from lunch with these guys today, and I heard the airplanes coming up, and I had to stop and look at them and see what they were flying. You know, you've got to like what you're doing. If you're in a job that you don't like what you're doing, my best advice is leave. Go find something that you like to do. You will not do a good job if you're doing something you don't like on a daily basis. Simple as that. You know, one of the reasons I like coming to Purdue, when I talked to the sophomores 15, 20 years ago, whenever I came here, I talked to the professors, and they always seemed to me like they wanted to teach engineers how to be engineers. You know, and my words here: engineers bring reality to science. Scientists bring advanced scientists, which I love them for. But you know, if you're an engineer, you know, I'm a touchy-feely kind of engineer. I like feeling stuff. You know, work on what you like to do, and if you don't, go somewhere else. But if you do one thing, engineering gets down to reality. You know, don't miss it. let's see if we can show the video. If you can't, I'm done.
All right.